Dear students, under the topic Graph Theory, here we have lecture 13. The topic is walks, trails, and paths. So, we are going to learn the theorems under walks, trails, and paths. The first theorem is in a graph G, any UV walk contains a UV path. So, in order to prove this theorem, let us first see the illustration for this theorem. So here we have a graph and we will consider a walk for this graph. So if I am taking the walk W as, so this walk represents from the vertex V1 and then the edge V1 V2 and then the vertex V2 and then the edge V2 V3 and then the vertex V3 and the edge V3 V4 and then the vertex V4 and the edge V4 V2 and then from V2 to V1 and again V1 V2 V2 V5. So this is a walk, it's a random walk. Now this walk will contain a path, so that is what we have to show. So here I have shown a path where it starts from V1 and ends at V5 as in the walk, and you can see that the path is V1, V2, V4, V5. So this path is contained in this walk. So this is the illustration. Now we shall see the theoretical proof for this theorem. We are going to prove this theorem by using induction hypothesis on the length of the walk. So what is the length of the walk? The number of lines in the walk is called the length of the walk. So we are going to prove this theorem by induction hypothesis on the length of the walk. Let us represent the walk as W and the length of the walk as P for this. So since we are proving by induction hypothesis, first we should take P to be equal to 0, which means that we are going to consider a walk of length 0. So how will be the walk of length 0? It will be just a single point, that is a single vertex. So if it is a single vertex, then W can be easily said that it is a path. So W is a path by itself because it is only a single point. So therefore the walk W contains a UV path. So now next we will consider the walk of length 1, that is the value of P to be equal to 1. And how it will be? It will be a single edge. So this is a single edge. So this implies W is a single edge. So if it is a single edge, you will have two vertices and one edge between them. So this is a path obviously. So therefore when P is equal to 0 and P is equal to 1, W is a path obviously. So the theorem holds in these two cases. Now since we are proving by the method of induction hypothesis, we are going to assume that the result is true for all walks of a general length n. And we are going to assume that it is true for all walks of of length lesser than n, and we have to prove that it is also true when the walk is equal to, that is the length of the walk is equal to n. So what we are going to do, the idea of the problem is we have to first assume that it is true, the result is true for all values of P lesser than n, and we have to prove that it is also true for P is equal to n. This is only the method of induction hypothesis says. So we shall first assume that the result is true for all walks of lengths lesser than n. So that is what we have written. We have assumed the result to be true for all walks of lengths lesser than n. So for all values of P less than n, we assume the result to be true. Now we have to prove that the result also holds for all walks of length n. So let us write that. So we are going to prove that the result holds for walk of length n, that is the value of P to be equal to n. Now in order to prove that, we are going to consider a UV walk of length n and we are going to represent it as capital W. So if you see here, we have considered a walk W of length n. So this is the walk U0, U1, etc. up to Un. Since we are calling it as UV walk, we are going to take the initial vertex u naught as u and the terminal vertex un as v in order to call it as a uv walk of length n. But the walk is u naught, u1, etc. up to un. And so this is the uv walk of length n. So now if all the vertices of this walk are distinct, then already it will be a path, because by definition we know that a walk is said to be a path if all of its vertices are distinct. So the walk itself will become a path, and therefore the theorem will be proved. So if all the vertices are distinct, so we are going to prove the theorem when all the vertices are not distinct, because the case is obvious when all the vertices are distinct. So let us just write it. So we have just written it. If all the vertices of the walk W are distinct, then it is already a path, and therefore the theorem will hold. So we are going to prove the theorem if all the vertices are not distinct. So how are we going to do it? So if all the vertices are not distinct, which means there will be at least one vertex which overlaps with another vertex, that is, it is the same. For example, we take two values I and j such that I and j lies between 0 and n. So we are going to take like uj, the vertex uj to be equal to, I mean ui to be equal to uj, because we are concerned with, we are saying that the vertices are not distinct. So we are going to take one such vertex, only one vertex which is same as the other vertex, because they are not distinct. So if we take like this, what will happen to this walk? Now this walk is from u naught to un, and from the 0 to n we are taking in between two values I and j. So in between somewhere you will have ui, and then you will have uj, and then you will have uj plus 1. So it will go on like this. Like this you will have in values in between u naught and un. So what we are going to do, we are going to take these two vertices as one vertex, because we are saying that the vertices are not distinct. So at least one vertex will be the same as the other vertex. So what will happen, instead of uj we will consider as ui itself, and then we will move on to uj plus 1. So this vertex we will neglect. So what will happen to this walk of length n? It will reduce it will reduce. It will be, the length will be reduced by 1, because two vertex are going to be same. So instead of walk n, this walk will become walk of length n minus 1. So let us write that. So this walk will become another walk w dash, where it will be of length less than n. So if we already know that by our assumption through induction hypothesis that the result is already true for all values lesser than n. So if you see here, we have assumed, let us assume that the result is true for all walks of length less than n. So therefore this walk will contain a path, that is a uv path. So since the result is true for all walks of length less than n, it implies that this walk contains a uv path, which is what we have to prove. And so hence we have proved the required theorem. So therefore in a graph G, any uv walk contains a uv path. So hence we have proved. So I hope you would have understood this theorem to the better of your understanding. So this is the theorem. In any graph G, a UV walk contains a UV path, and this is the illustration. Thank you.